Everything we've talked about so far has had to do with how intermolecular forces impact the boiling points of molecular liquids. We're going to do a series of videos that are very short here, where we, instead of looking at boiling point, we look at other properties of liquids that can be impacted by uh, intermolecular forces of all types. This is something we're going to start with is surface tension, something you probably have heard of before, and something that you can actually do at home when you have a minute. If you get a glass of water out and you find yourself a paper clip, an interesting thing happens if you're very careful. You can actually place the paperclip on top of the surface of the water, and it will essentially float on top of the water. This shouldn't happen. A paperclip is more dense. The substance that paperclips are made out of, whether it be steel or aluminum, is more dense than liquid water. And so that paperclip should sink to the bottom. And in your first few attempts, it probably will. But if you get out a pair of tweezers and you are very careful, you can essentially lay that paperclip on top of the water and it will stay there. And I think the diagram on the left-hand side of this picture does a good job of explaining why that is. If you look at it, the orange spheres are supposed to represent a simplified version of a water molecule. And in essence, what we have is a situation where all of the water molecules that are on the interior of the beaker, so for instance, this one right here, those are experiencing intermolecular forces in all directions. That water molecule in the center is being pulled using hydrogen bonds to the top and bottom and left and right and northeast and southeast and every direction you can think of. It is being pulled. Okay. So the net effect is it's really not being pulled anywhere because it's being pulled everywhere. On the other hand, if you look at the surface layer of water molecules, they experience something totally different than the water molecules on the interior. A surface water molecule, like the one with arrows on it, is pulled left and right and all directions down, but it's not pulled up because there are no water molecules above it pulling on it. And so the net effect is that the surface molecules are kind of pulled in and down. I don't know if you were a kid, when you were a kid, if you ever in PE or music class ever did the parachute with your classmates. Do you know what I'm talking about? The whole class stands around holding onto a parachute and you can pull off all kinds of little tricks with it. One of the things that you do is you let it kind of billow up and then pull down really hard on it, and the fabric becomes really, really tight. That's essentially what's happening to the water molecules on the surface of this sample of water. They get pulled in and down, and so the surface molecules are essentially closer together and tighter than water molecules on the interior. It essentially gives the surface of the water kind of like this elastic feel to it. You can even see that elasticity in the picture on the right with the paper clip. See how the water looks dented, but it's not breaking? That's surface tension. And what does this have to do with intermolecular forces? Well, the network of forces that are holding all of those water molecules together and pulling those surface molecules down, that's hydrogen bonding, right? So you can, if you go to the lake this summer, look at water bugs, for instance. They should sink, but they don't. They sit on top of the surface of the water thanks to surface tension. In addition to that, Its surface tension explains why water forms droplets. Again, all of the water molecules on the exterior are pulled inwards towards the middle, and that naturally on its own gives us a spherical shape. I'm going to show you another video here in a second that's really, really cool and gives you a true sense of kind of the stickiness of water that comes along with hydrogen bonding and surface tension. Until then, I'll see you next time.